Good evening. Welcome to this public lectures organized jointly by Institute for Medical Science and Department of Physics at NUS. As part of our research outreach program, our institute organized public lectures. The objective of our public lecture is to raise public awareness and understanding of the role of mathematics in science, engineering, technology, and industry. Today, we are very pleased to have Professor Christopher Foote to deliver a public lecture, Quantum World of Ultra-Cold Atoms. Let me give a brief introduction of Professor Foote. After having begun his physics career with a first-class honors degrees and doctorate from the University of Oxford, Professor Christopher Foote spent several years working at Stanford University, supported for part of the time by a Lindemann Trust Fellowship. He returned to the Oxford Physics Department and started research on laser cooling and trapping of atoms. Since 1991, he has been a tutorial fellow at St. Peter's College, Oxford. His current research interests include the study of the superfluent properties of ultra-cold atomic gases and experiments on ultra-cold atoms held in arrays of optical traps formed by laser lights to study the quantum properties of the many particle systems. Such atomic physics techniques gives very precise control over the cold atom systems so that they can be used to simulate phenomena that occur in condensed matter physics and in the future for quantum information processing. So let's now invite Prof. Foote to deliver his lecture, The Quantum World of Ultra-Cold Atoms.
Okay, thank you very much for that introduction. It's a great pleasure to be here in Singapore. It's a very nice planet, it's a very nice place. As I was saying, I've only been here once before, just stopping at the airport and passing through. It's nice to get out and see what a nice place it is. And thank you for the invitation from Wai Tzu Bao to visit the Institute of Mathematical Sciences. And I should also thank Jiang Ping Gong, who's helped me prepare the demonstrations that I've got here. So the lectures are really intended for the general public or non-experts in the field, although I noticed some of the experts have come as well. I hope they enjoy it. Okay, so what I'm going to do is to tell you about the subject of cold atoms, which, as you've just heard, I've worked in for a number of years. And this is a sort of very fascinating field where we've tried to use lasers to cool atoms to very low temperatures. And in doing that, we've found out some sort of very new things. And it's been amazing to me, I feel fortunate to have worked in this field, where every few years there's been something, new techniques, as often happens, lead to new discoveries and things that just weren't dreamt about when people started off on this direction. So hopefully I can tell you about a few of those things this evening. Okay. So just briefly, what I want to actually cover in the talk then is first of all to introduce some idea of what we mean by temperature. And as I said, this is sort of the non-expert, so start right at the very beginning. And then how we actually then use laser light to cool atoms, which may seem slightly contradictory, but when we use laser light we can actually get to lower temperatures, and I'll show how we can get very low temperatures. And then when we've done that, we find that we actually get to a regime where we have quantum effects, which are very interesting, and I'll try and convey without any mathematics some of the interesting things that have been found there. So first thing then is to think about temperature a little bit as an introduction. And of course what we mean by temperature is a bit subjective. I mean, a cold day in Singapore could perhaps be the hottest day that we have in England during the summer. Probably this summer, that's probably true. So we need some method of measuring temperature, and of course everybody is familiar with this. Well, actually perhaps a rather old-fashioned type of thermometer now, which is based on the expansion of mercury. So we have mercury in the tube that expands up and down. And for just the way that people agreed to measure temperature was the following: that put this in a bucket of ice. This is a freezing point of water here, and we make a mark and we call that 0. We put it in boiling water. Here it's being heated up by a little burner, and then we make a mark up here and we call that 100. We make 100 units in between, and that's then what we mean by the Celsius scale of temperature. And that's what everybody knows and uses to know what the weather is going to be and so on. But this is not actually so good for us as physicists. Well, I mean, we can use it for everyday things, but if we want to measure very low temperatures, then if we want to measure very low temperatures, then what we actually need to do is to have a different method. And what we use is the expansion and contraction of gases. And I got a demonstration of that. As I said, it's for non-experts here. So probably you all know that gases do expand and contract. So I've got a balloon here which has got air in, obviously, and now I'm going to cool it by with liquid nitrogen. So liquid nitrogen is basic air is mostly nitrogen, with some oxygen, obviously, that we breathe. And if you cool liquid nitrogen down to minus 200 degrees C, it actually becomes a liquid. So this stuff is at minus 200 degrees C. So if we put this onto the balloon, so this is the just ordinary cooling. Let's see what's happening. See what we get. Right. So actually, it's not very. Normally, what I do is to push the balloon into this that you can't see in this particular bucket. So we'll start off by having it very cold, and you can see it actually has contracted. So when you cool things down, then like the balloon, then they will contract just like the mercury contracted, and then as it warms up, it expands. So let me just do that one more time. Right, we find the blue. It's got yellow colours as well. So this one. So the important point to note perhaps about this is that when I take this out, it's actually completely collapsed. It looks like there's nothing in here, and then it starts expanding again. And oh, I see. And that's what happens to an air balloon. If you actually want to, I think that one was actually first. So if we were to do the same experiment with a helium balloon, then we'll find that although it will well, let's just see what we find. If I can get it in there without freezing my fingers. I don't actually see it very much. You can see it there. So what will happen? The helium is obviously contracted as well, and you can see it expanding there. But the helium doesn't actually collapse. And that's important for what I'm just about to say. Okay, so that's the demonstration. You can look at that after the lecture a bit more closely if you want. So that's a sort of simple demonstration for sort of general illustration, but actually, obviously, as physicists, we want to do this a bit more quantitatively. So what people do is usually have something like this, which is a sort of a cylinder or a chamber, where we've actually got a gas of particles, which are represented here as these dots flying around, and we have a barrier here that can move in and out. So when the thing is hot, when these are moving very fast, then it will have a large volume. And when we cool it down so that things are moving slower, then this will move in. So this is free to slide in and out. We're not pushing on this, we're just letting it slide in and out. And that will have a smaller volume, just as a balloon had a smaller volume. And we can actually then plot a graph here where we plot the volume, or the size, versus the temperature. And in fact, obviously, we have more than 2 points on it. If you've got 2 points, you're bound to get a straight line. But if you have many points, you find it lies on this straight line for most gases. And as you keep coming to lower and lower temperatures, it looks like you're actually getting to a point where you've got no volume. But if you've got a real gas, like the air in the balloon, then you find there's a point where it suddenly becomes a liquid and collapses. Because this was liquid nitrogen, the air was actually liquefied, so it collapsed to nothing. But if we had a helium, as you saw, it actually goes down and doesn't collapse. And actually helium, you can go much lower volume, but eventually it will become a liquid. But if we can imagine that we have an ideal gas, a gas that didn't become a liquid, then it would still go to 0 volume at some value here where this line meets the axis. And this is at minus 273 degrees Kelvin, sorry, degrees centigrade, which is then the lowest temperature really that we can get to, because beyond that the volume, well, the volume will be 0 and we can't go any further. So that actually then is what we call the absolute 0 temperature, the lowest temperature that we can get to. And it's a bit inconvenient to call it this number all the time, slightly more decimal places here. So we call that the absolute 0 and define new, the cat out the bag earlier, the new temperature scale called degrees Kelvin. So this will be 0 degrees Kelvin, would be this number of degrees C. And then we can measure up from there. And 1 unit of Kelvin is the same as, degrees Kelvin is the same as 1 degree C. And so the temperatures I'm going to be talking about in the lecture of a millionth of a degree Kelvin and below is a bit inconvenient to write as degrees C, but it's just quite convenient to see that it's really very close to this absolute lowest temperature that we can get to. Okay, so from that we can see that I've said that when we say things are hot, they're moving very fast. When they get colder, they move more slowly. So that might mean that when we get to absolute 0, they must be stopped. Is that actually true? Well, it's actually to a large extent true. And certainly before quantum mechanics came along, that would be the picture that people would have for, as you cool things down, they came to rest, and that was the lowest temperature you can get to. But in fact, and this will be important later in the talk, you can never actually get a particle or an atom to completely stop when it's got a finite amount of energy, because we never know exactly where it is. It's actually got a principle that says that. And as I say, that will be important. These quantum mechanical effects are important, and that's what I'll really be talking about in the later part of the talk. Okay, so I've introduced what the idea of temperature is, and now I want to say how can we actually get down to these extremely low temperatures. And this, as I said, it said at the beginning, the abstract is actually using laser light, which is so how do we use light to cool things? Obviously, if we go outside, here, especially here in Singapore, we feel the light heating us up. So we feel the energy, get the energy from the sunlight falling on us. But light also creates a push. It also pushes on things. But actually, when you go out, as I say, even here, you don't actually feel something push down on it, because the force of light is in fact extremely small and it's pretty unnoticeable, except in special cases. And one particular case where you do see it is in astrophysics. So there's 2 actual examples on here. If you actually look in a star, then a star like the sun is actually sending out a lot of light, obviously, and that light going out stops stuff collapsing in. That's one important thing in astrophysics. But obviously, the more important thing in this transparency, or the slide here, is the comet. And a comet is something that's, it's not a shooting star, not something burning up in the atmosphere, but a comet is a ball of ice and dust that's sort of orbiting around in the solar system. And it has a tail here that goes out, and that tail is made up of little dust particles that are being pushed off. And the tail is pushed away from the sun by the force of the sunlight. So it's not actually, as I say, like a shooting star where the tail goes behind it, but you can actually see that this tail always points away from the sun. And as shown here, sort of the dotted line representing the orbit, the tail always points away from the sun. And so that's one example in astrophysics of this force of light. But in the lab, we can actually see this if we use lasers and sort of setup that we use for cooling atoms is shown here. So if the atom is going towards the laser, then the laser is pushing on it and actually producing a force that slows it down. And there's a demonstration of that we've got here. Reload that. Okay. So what you can see there is a, well, I was still having it first, is representation of a laser with the atom. We're actually missing the atom at the moment, so it comes along. And the laser is firing out little balls which represent little lumps of light, little photons. So if we, sorry, I've got to get the laser in the right place. Okay, so now those are hitting me, and each one that hits it gives it a kick in the backward direction that slows it down. And you can see actually it's reversed. That's actually one problem. So let's do that again. So the idea, that's what we want to do. We want to put the laser light in the direction opposite to where the atom is going and slow it down. So I think we've seen enough of that probably. Okay, so that's how it works. Or you can do it even faster if you want it to turn out there. Okay, so that's the essential point of the simple picture of laser cooling. Okay, so if we actually do that in an experiment, it looks something like this. We have up here a box, which is called an oven because it's usually heated up if we want to have a metal in there, with a little hole in it. And there's a gas of atoms in there, and they come out and form a stream of atoms coming down in this direction. And if we look at the speed or the velocity of those atoms in this particular direction, then we see a graph of them is something like this. So there's some sort of tip, because they're all going in this direction, they all have positive speeds. So there's some mean average velocity around here, some sort of bell shape or spread like this. So there's some fast ones and some slow ones. But that's the sort of typical speeds they've got up here. But if we look down here, when the laser's been pushing on them for a while, then we'll see something typically like this. This is just an artist's impression, actually. So what you can see is that the atoms that started off with this velocity have slowed down and they've moved over here, and there's a pile over here. But we haven't actually pushed it down towards zero velocity. And the reason for that is that the Doppler effect. The atoms only absorb light and get pushed on if they've got a very particular velocity. Once they change velocity, they no longer sort of feel the force of the light. And because that's so important in this context, I wanted just to briefly explain what I mean by the Doppler effect in case people weren't familiar with that. And in particular, probably not that familiar with the Doppler effect for light, but I guess most people will be more familiar with the Doppler effect for sound. It's quite easy to illustrate. Basically, the Doppler effect arises when you've got something that's making a sound and it moves, and you hear that the sound has a different pitch to when it was stationary. So I'll switch this on, it's a guitar tuner. So it's making a noise. And if I just wobble it around, you shouldn't hear anything. But if I move it towards and away from you, you should hear the note change, I hope. I don't know whether I can move it fast enough. Does that actually make sense? So when it moves towards you, it should go to higher pitch, and away it should go down. Does that? People hear that? Yeah. Okay. So that's one illustration that people may have heard. Another one I actually found on YouTube, which is quite interesting. So, it's all right. Need to turn up the sound. Okay. So, I think I should have played it before. So this is a fire engine that you can hear, and you can hear the note as it's coming towards you. And as it goes past, you should hear the note change. So that's a classic illustration of the Doppler effect for sound. Usually on physics books it's to do with a train going through a station, but that seems to be quite easy to hear in that particular case. Okay, so the Doppler effect for light is actually more difficult to illustrate. So if I have this red laser, I shine it at you, which I won't do, but it's red. But if I try to move it, you won't see it change colour because I can't move at anything like the speed of light. And obviously, you've got to move, so it turns out that it's harder to, well, you have to move faster to see the Doppler effect for light. Sorry, we'll move back to that one, okay. Oops. But you do see it in, for example, stars. But if we want to see it in the lab, we can see it for atoms, because atoms actually are very particular about what frequency of light they absorb. So if we go back to this one, then these atoms here, when they change their velocity slightly, as it were, the pitch, if you imagine this was sound, if the atoms are moving towards a source of sound, as they change their speed, they hear the pitch change slightly and they stop absorbing the light and feeling the push. So that's what happens. Basically, the Doppler effect means that only a very particular velocity gets pushed on. So how do we get around that? This is an experiment that was done. There's lots of experiments, not the first experiment, but it just happens to be one I got the picture for. So what we do is we actually take the laser frequency and we sort of move it to keep track of the atoms as we slow them down. So if we have an atomic beam, like I think it's me, isn't it, when I turn around to the speakers, that funny sound. So I'll just look over my shoulder. Start off with this spread of velocities given by the dotted line, and then we take the atoms here and we push them to a lower speed, and then we keep pushing them and pushing them and pushing them. We eventually pile them up here. So what we've actually done is to take some atoms which are going to moving quite fast and reduce them to zero velocity with this nice narrow spread. And in fact, the Doppler effect isn't actually a problem. It turns out to be quite helpful, because if you didn't have the Doppler effect, what you do is you actually sort of just take the whole original spread and push them over towards zero. But here, because the atoms stop interacting, unlike when I showed the ball being slowed, it sort of got pushed backwards. It was stopped and then pushed backwards. Here you can actually bring them, and then the Doppler effects, they stop absorbing the light, and you get this nice peak there. Okay, so in simple terms, what we've done is to start off with things that are moving at sort of speed of sound, supersonic type, or faster, that's speed of a jet plane, and then cool them down, and we can get to typically these sorts of velocities, so they're moving really, really slowly, just crawling along. And that was a big breakthrough in the field, and for that these people were given the Nobel Prize in '97. Broadly speaking, Bill Phillips was sort of started off laser cooling by slowing atoms, which I just described. Stephen Chu then developed it further. He actually put laser beams in all directions, so that it would cool whichever direction the atoms moved, they were slowed down. And Claude Cantalucci did a lot of theoretical work which described what was going on. Okay, and this is just to remind me to tell you that what I'm talking about here is actually cooling of gases. And of course there are other ways of cooling things like refrigerators, and of course they're used in many experiments to cool solids and liquids. But we're talking about cooling gases here. But I put this in because I'm sure if I didn't, then people would just go away thinking laser cooling, well, we can cool everything to a millionth of a degree Kelvin. It's actually only gases, and that's what, as I say, the prize in '97 was for, the Nobel Prize. Okay. Okay, so I've now described how we can slow the atoms down, which is actually cooling them a lot. Now we want to think about how can we actually confine those atoms. Once we've slowed them down to these very low velocities, we can't just put them in a bottle or a container like that over there, because the walls of the container would be much hotter and they would heat it back up. So we want some way of trapping the atoms. And the way that's done is actually using magnetism. So we don't want to actually, we just want to hold the atoms in free space, well not in free space, inside a vacuum in fact, but hold them without touching them using magnetic fields. And it turns out to be a device that illustrates this very nicely, which is called a levitron. And if we're lucky and it hasn't changed the temperamental, it might be able to demonstrate it. Okay. So I'll zoom in on it, or I was going to just do this. Okay. So, got the camera on it? No, it's okay. Right, so what I'm going to do is to take this, it's a small magnet here, small magnet here, and it's actually, there's a magnet in this base here, which is repelling this one, but it only repels it when it's this way. If I actually just let go of this, I can be a bit delicate because I don't want it all to move around, I'm supposed to say that, but what you'll see is, as I let go, it actually just falls over like that. So you can't just push it, let this, so it's repelling it and have it stably like that. What you've actually got to do is to spin this, just like you have a top on a table spinning, it'll stay upright. So if we spin this, then we can actually get it stably balanced, possibly. And this device here is a bit different. There used to be a device where you could just flick it with your fingers, but this new device is more difficult to set going. So I'll see whether this works. So this is just spinning it up. And then I've got to lift it up gently and it may stay balanced like it is. Okay, so what we've actually got now is this magnet spinning, and it's repelling from the magnet that's around in the base here. And, well, yes, okay, that was, well, I think you saw it. I'll just try it once more. It usually goes a bit longer than that. But, my hands are quite so steady. Okay, so there we are. So it has to spin. Right. Okay, well I think you've got the general idea then, right? So go back to this one. Right. So how does that apply to atoms? Well, we want to use magnetic fields to trap atoms, and indeed atoms can be thought of as little magnets, which are, and they have a particular direction of their spin. And that's just a picture of that in case, I guess in case it didn't work, but we didn't have a camera. So it's just the levitron sitting there stably. This is the old version. Okay, so to apply that to atoms, we don't actually use permanent magnets, but we use the magnetic field that you get from currents in a wire. And actually what we do is create this sort of like cage-like structure. This is actually a picture of somebody else's. And so these wires have currents going in the direction indicated, and the atoms are trapped very stably just at the centre here, just as that levitron was held above there. In our actual experiment, we have something like this, a slightly different configuration, but the atoms will be trapped right in the middle of this cage of current-carrying wires, producing a magnetic field. In the actual experiment, we have a glass cell which holds the atoms, which is pushed in, sort of shown. So there has to be a very high vacuum, because again, we can't have sort of the atoms in the air colliding with the cold atoms. So we can get these very cold atoms trapped there, and these have got very big current-carrying wires, hundreds of amps go through here. They're about, this is a scale, they're about an inch across, and it's all sort of water-cooled. So that's the magnetic trap that we use to hold these atoms. And it turns out then that once we've got the atoms in the magnetic trap, you can actually cool them even further by simple evaporative cooling. That is, you just let some of the hot atoms escape, and the ones that remain get colder. And I've got a demonstration of that as well, I think, somewhere. Oops, I was on that one. I should have turned it down. Right. So, I mean, the simplest example of evaporative cooling is perhaps if you have a hot cup of tea, or this is from America, so it's probably a cup of coffee, and blow away the steam. You're just taking the hot atoms away faster, and what's left gets colder. But also on this, this is the Physics 2000 website. They have this very nice illustration of evaporative cooling. So I think actually it's been running for a while, so let me just reset. Okay, so what's represents here is a lot of atoms inside a magnetic trap, so that U-shaped thing, bowl, is a representation of the magnetic trap. And you put in some hot atoms, and they're bouncing around, and so on. And to make the gas colder, then what you do is you let some of them escape. So if we do this, and the hot ones escape, and the ones that remain get colder and colder and colder. And so, and eventually something quite dramatic happens when you get to a certain temperature, and that's what I'm going to talk about in a minute. You just want to see that again. So there's various other things shown here, which you can look at that for yourselves if you want on this website. But basically, evaporative cooling is just letting the hot ones go and you reach a final temperature then where we actually, not at absolute zero, but something, oops, I think I've gone a bit fast there. I wonder if it's going to happen. Okay, I think my hand was a bit wobbly then, I only got one atom. I think it's a sort of game that you can play, and I think you're supposed to get, I think the one is about the minimum you can get in that game. But under other circumstances you can do better. Right. So we talked about how we can cool things by evaporative cooling, and I said something dramatic happens when you get to a certain temperature. And that's basically when we enter this quantum regime, and we stop, we need to think about what the gas is in a different sort of way. And I'll try to explain that in a non-mathematical way, which is probably quite difficult, but just involves a lot of hand-waving, but I'll be happy to answer questions afterwards. So here's a picture of it anyway. At room temperature, we'd be thinking of a gas as lots of little particles bouncing around quite fast. But as we cool it down, we can no longer really think of the atom as being just a point-like particle somewhere. We have to start thinking about it as a sort of wave, because atoms in quantum mechanics have this sort of dual nature. You can think of them as particles and waves. And that in particular, then they're usually represented as these little sort of bits of waves, or wave packets actually, they're often called. And so they actually, rather than being point-like, they have a certain spread. And then as you cool further, these waves get longer, get more spread out, and so there becomes a point where the waves sort of overlap with each other. And that's the critical point where it was represented by that some sort of change in the evaporative cooling demo. And that's where the atoms really, when they're overlapping with each other, you can't think of them as individual atoms anymore. You've got to think about them as sort of one single entity. So you can't tell which atom is which anymore, so it's no good sort of thinking about them as little billiard balls. But once they overlap, they really become sort of one quantum system. And that's represented here by sort of overlap and becoming one big wave. And so as you cool further and further, they actually become, as I say, a single entity, which you can represent as a sort of wave-like thing here. And indeed, in quantum mechanics, we talk about the wave function of the system. You know, it is represented as a wave rather than lots of individual particles. And in the particular case we're going to talk about here, this change into the quantum regime, at that point you see this phenomenon called BoseEinstein Condensation. And let me just try to explain a little bit about that. And that was a big breakthrough in 1995. And one of the, and that was the first Bose-Einstein condensate was seen in Gila and Boulder in Colorado. And what they've done then is to evaporatively cool atoms in a magnetic trap. And actually, at a certain point, they underwent this dramatic change, which I've shown here. And actually, one of the most dramatic things about it is perhaps that the field produces these very nice pictures, rather than sort of graphs and points and just jump on some sort of line. You actually get these very nice pictures. I think that was is a very nice aspect of it. So what have we actually got here? This is actually there's three pictures of a cloud of atoms, but rather than just saying we could just show a cloud of atoms as a black and white image. That was a bit boring. So what's actually been done here is to change it into a graph. So in some sense there's sort of white round here where there's no atoms, and then there's the density of atoms is represented as a sort of the height. So this is a lot of atoms. So this is just a blob of atoms. And this one is just atoms that really can be still thought of as particles, so sort of ordinary gas. And actually in our lab we sometimes call these hot atoms, although they're actually less than a millionth of a degree Kelvin. But they're the ones that really can be thought of as bouncing around on billiard balls. And if you cool them a bit to half the temperature, then you start to see that in the middle you get this peak rising up. And as you go even further, you get to the point where that peak, all these sort of atoms in the cloud, which are individual atoms, have gone, and this peak has risen up. And this is now when this is where the atoms are starting to overlap with each other, and now this is where they're sort of, as it were, completely overlapping. And so we don't think of the individual atoms, but one giant wave. And as I say, in this field, the nice thing is you sort of see things directly. So in some sense, this is the way you've seen it. It's been released, so it's expanded, but it's basically looking at almost the wave function of the atoms. And if you actually cooled further, you wouldn't actually see it go any narrower. You just actually lose atoms. And this is because, as I said, at the beginning, we've got now to sort of effectively as close to absolute zero as you can go in some sense, because now it's quantum mechanics that's causing this spread, not actually the temperature. They always want to have a certain spread, and so this is the minimum spread that you can get. And so that was a great achievement. And here's the picture of the people who did it, Eric Cornell and Carl Wyman smiling, and a picture of the peak in his hands here. And so the point of this slide is to say a bit more about what Bose-Einstein condensation, where it came from. It actually came from Bose and Einstein. And the story, briefly, is that Bose, who was an Indian physicist, did some work on light, sort of effectively when it was cooled, some sort of calculation, and it was perhaps a bit too novel, he wouldn't understand it, and he couldn't get it published. So he sent it to Einstein, and Einstein realized it was important and helped him to get it published. But Einstein also realized it could apply to, just not to light, it could apply to atoms. And he predicted then that as you cool things down, at a particular point, there would be this thing that's become known as Bose-Einstein condensation, which we saw in the previous transparency. And I think the important point to realize is it's Bose-Einstein condensation in a gas. The name condensation is perhaps a bit misleading because you think of then steam becoming water on your window pane or what have you. That's what we call condensation, but what they meant here was that you change from an ordinary gas to sort of a quantum regime. It always stays a gas throughout, that's the whole point. And I mean, there had been hints of things like Bose-Einstein condensation in different systems, but this was the first time in 1995 it was really seen just as Einstein and Bose said it would. And it turned out to be very close to what they said. And for that work then, these people, Carl Wyman and Eric Cornell, got the Nobel Prize, with Wolfgang Ketterle, who did a lot of the work on understanding the very fascinating properties of this Bose-Einstein condensate, and that's some of which I'm going to try and explain now. Okay, so basically, as I said, when you cool things down, you can no longer think of them as sort of particles bouncing around, but they've got more wave-like properties. And if you're not so familiar with waves, then a really good representation is water waves, where you see here a source of ripples going out, making nice circular waves. It's a very simple example. If we actually now go to have two sources, and I think this is probably something most people, certainly most people doing physics will have seen, because it's a sort of standard school experiment, probably over here as well, I should think, isn't it? As well as in the UK. So this is where you have two sources now of waves, and you can see as they go out, there are places where the waves arrive together, and then you get an extra big wave, and places where where the trough arrives on the trough arrives where the peak of the other one is, and so you get no net, nothing happening. This is a computer simulation of that. Okay, so that's just actual from this Physics 2000 website, just a nice demonstration of that. So this is two sources of waves moving out, and you can see there are places where you get a strong wave and places where there are no waves. And anybody who's familiar with waves will find that not very surprising. But now let's consider what happens if we take two sources of atoms, as it were. If we took two clouds of atoms and let them overlap with each other, then what you'd really expect is that obviously just be more atoms in the middle. But this is an experiment that was done by Wolfgang Ketterle at MIT, and where he took two Bose-Einstein condensates and overlapped them. And he didn't see that, he saw this. So actually, you see that the atoms forming in this pattern like this. So actually, if you think about it, what's happening is if you had just one of these Bose-Einstein condensates, then you'd have a blob of atoms. So you'd have atoms here, whereas there are no atoms. Sorry, white is where there are no atoms, and dark is where there are atoms. This is you can actually again put this as a nice colour picture, but this is more like the raw data here. But now, where there were atoms before, and if you put a second condensate on top, overlapping with the first, then there are no atoms, and there's sort of more atoms in the other place. Just like here, when you've got waves, there are places where it's strong and places where it's weak. And this was then, as I said, done at MIT. That was a sort of very dramatic picture that was obtained soon after the EC was first created. Another thing that we can do, this is work that we've done at Oxford. Sorry, I couldn't resist this quote. This is vaguely relevant. This is a quote from Tolkien. The relevant bit is one ring to bring. Oh, I missed out two. One ring to bring them all, and in the darkness bind them. So this is a trap now, where this is actually sort of now just a dent. It could be black and white, but we've made it coloured so there are certain colour schemes. So it's densest here, and you see no atoms here. We're combining atoms in a ring, basically a BoseEinstein Condensation in a ring. And why we want to do that is, again, because of these wave-like properties of the atoms, that ring traps have particular interesting properties, because you have the waves going around the ring and joining up with each other. So if we actually go here, what the atoms like to do is to sort of, they're represented like a wave, and they want to be like they're joined up with each other, and they don't want sort of this situation where they got a bit missing here, so they tend to be like this. So if we actually get the atoms moving around, so they're represented by a nice wave here that's all joined up, then they want to keep doing that all the time. And they won't actually want to slow down, because if they slowed down, then they would actually have to go through a situation a bit like this one. So once you actually, although it's difficult to get it going, once it's actually going, it will actually keep going almost as long as the atoms are there. And we call that so-called superfluid flow, where super means obviously it's some sort of special behaviour. And so, whereas if you had an ordinary liquid, like water in a sort of ring-shaped pipe, then obviously if you set it going, it would quite quickly stop because of friction. This superfluid actually has sort of effectively no friction, will keep going around it. And that's another nice property of those condensates. And its super behaviour is also seen in current-carrying wires, so people might be more familiar with superconductors, where now electrons flow around in a loop without decaying. And that's useful, for example, in superconducting magnets. On a larger scale, you can actually get superconducting magnets like this. It's actually a picture of from Oxford Instruments. One of these magnets being used for MRI imaging. This person sort of seems to be reluctant, but he's being pushed into the strong field of the magnet. And there's a superconducting wire around here, and the current goes around there after it's set up for a long, long time. And in fact, it would be very expensive and costly to keep providing the electricity if it wasn't a superconductor. To get, it would be very difficult to get these fields for this particular application. Okay, so then I've got to describing some of the sort of properties of the BEC. Now let me, I just wanted to say before I go on to the next part, can we actually get anything to Bose condense? If we cool any gas, will it undergo Bose-Einstein condensation? And the answer to that is no. There are actually two types of particle that we can have in nature, and only one of them will Bose condense. So there's one type of particle are the bosons, obviously named after Bose, of Bose-Einstein, and they're the ones that we've been, type of atom that we have to do these experiments with, and they want to sort of go together. So when they overlap, they all form sort of one big wave, and that's the phenomenon we'll be talking about. But there are fermions, which are actually unfriendly particles, as it were. They always want to sort of avoid each other, and so they actually won't overlap. But they're actually, the reason why the Bose-Einstein condensate was such a sort of interesting thing was there are not really many examples of this behaviour. I mean, there are some, but not so many. But with fermions, then that's actually really quite common. For example, electrons are fermions. And so if you do your sort of elementary chemistry, then you build up a periodic table, then you see that's important. So you have hydrogen with one electron. Helium, you actually have two electrons in the same shell, but they're spin up and spin down, so they're not exactly in the same state. There's sort of two flavours. But now when you come to put the next one in, that can't go into this shell, so it goes up here. If these were bosons, they'd all just pile up in the bottom shell, and, chemistry, things would be very different. So fermions are wanting to stay apart, whereas the bosons, once they overlap, they all come into this sort of single quantum entity. Okay, so I've now described the sort of BoseEinstein Condensation. Oops, right back to the beginning now. Right to the Bose-Einstein condensation and some of the properties of it. I wanted to say a bit more now about the sort of recent things that have been done using the BEC. And as I said at the beginning, some of these things just weren't predicted or weren't dreamt of when people first started, laser cooling and then Bose-Einstein condensation. And then well, these latest experiments just sort of come about in the last few years, caused a lot of excitement, which I'll try and describe. So what we can do is actually to make atoms up now into sort of crystals. So having cooled them down, we can now start sort of moving these atoms and building them up into structures. And to do that, I have to introduce a different type of force on atoms. So far I just talked about the one type of force, which is the sort of laser beam pushing on the atom to slow it down. I want to introduce now a different way that light can affect atoms. The one that is a non-technical talk, so I call it the sideways force, rather than sort of the pushing force, which goes along the laser beam. And I try to illustrate how that arises, shown here. So what we have is this sort of, to come out a bit dirty orange, but it was red, I think, at one point, is a laser beam going across the middle here. And a laser beam is not sort of the same intensity all the way across, or the same brightness all the way across. It tends to be bright in the middle and fall off to either side. So if I plot the intensity here, it sort of has a bell-shaped curve, starts very bright in the middle and falls off. And so that's a laser beam. And what I've shown is that it's actually shining on a lens, rather than drawing for an atom. Just imagine what the force is on a lens. You can imagine the lens is very small if you want, but it doesn't really matter to the argument. So this is a glass lens that's bending the light. So we know that light is bent and it comes to a sort of point where it's focused over here. But that's not the important point here. The important point is that the light is bent. And if you have light that's coming along and it's bent, it changes direction, then to actually make it change direction, you have to exert a force on it. And if you exert a force on something, then you yourself will feel a force backwards, a reaction to that. And again, I'm sure that's completely familiar to anybody who's been doing physics, but for the sake of anybody who's not familiar with that, I've got this picture here. So this it just shows basically Newton's laws. So if you imagine that you're on a water slide going down in a certain direction, so you're coming down here, then obviously if the slide wasn't there, you zoom off over here. But the slide is there, and the force of the slide acting on you pushes, hopefully stay in it, go round in a curve like here. So that, you actually feel that when you're in it being pushed on, forces that way. So the force on the slide in the opposite direction, because this is a reaction to that. So obviously, if the scaffolding wasn't there, then the slide would wobble around as people went down it, because there's force pushing outwards. So what we're saying here is that if we take light that's going in a certain direction and we bend it round, then there's a force, whatever bends it round feels a force in that direction. And so the light is bent here, and there's a force in that direction. And similarly, this ray is bent, so there's a force in that direction. But because it's much brighter here, then this is a bigger force than that one. So we can see that we're actually getting a pull, which is pulling your lens down in towards the laser beam. So the lens, it's not just pushing, there is a pushing on it in that direction, which is what we sort of more obvious. But here we've got this sort of slightly subtler effect of pulling it towards where the intensity is highest. And if we reverse the lens, we have a different sort of lens where it's diverging, where the glass is convex, then the direction of the force is reversed. So it's actually a sort of more controllable force than the other one. So just pushing on it, it actually can go in both directions. So that's a sort of non-technical introduction. What we actually do in the experiments is rather have a situation where we have laser beams that come in from all sides, and we make a pattern of light that looks like this. So, and then what happens is when we put the atoms in here, they want to move to the region either where the intensity is highest or where it's lowest. So when we put them in here, they actually sort of get held in this situation. So how do those how does that pattern form? If we just go back to this thing that I talked about earlier, where you have two sources of now water waves, you have places where there are no waves, where they sort of cancel each other, places where it's strong. If this was light, then these would correspond to places where it's dark and places where it's bright, so we'd have something like this. And this would be from the two sources. So what we have here is four sources, four laser beams coming in, and so that sort of adding up and cancelling out results in this sort of pattern of light here. And it's also then, because the atoms are going towards where the intensity is higher, where it's low, it's also the sort of, represents the sort of surface that the atoms move on. So you can think of it just like an egg box for atoms, which is written up there obviously. So you can put the atoms in there, and then they'll actually settle down and be held, say, in these little dips. And people did that experiment, and I guess this is what you might have expected if you took a BC and you put it into that egg box sort of potential. But the remarkable thing was that, well, they did see that to start with, but under certain conditions, and I can't really go into it in too much detail, you can actually make it go like this. You can actually get those atoms through sort of quantum effects to spread out evenly so that there's actually one atom per site. So now we've gone from having this cold gas in the BC to actually something that looks really quite like a crystal, where you've now got this cold matter arranged regularly, and so it's a sort of crystal of atoms that are held together by the laser beams. And that has led to a lot of exciting things. One of the things, so I just passed, it's not really a general transparency, but it just shows the sort of thing that we've been doing it, or trying to do it also, which is along those lines. So have a sort of vacuum cell where we have the atoms. Instead of having it in sort of the middle of the vacuum, we have it on the surface here. So we have laser beams coming in and forming this sort of egg box potential here on the surface, so we can put our atoms in that. And if we have them then with a lens here, which forms part of a microscope, eventually, say it's in progress, not something we've seen, we might see something like this, see those individual atoms. And so in this way, with a sort of microscope, you could actually make, as it were, cold quantum matter and actually look at it, visualize what's going on, and do things like that. And they can actually then extend that to 3 dimensions, have all laser beams coming in from all directions, and create a sort of almost perfect crystal like that, again held together by laser light. So what people say is, well, we've basically got a system where we can have designer matter. Just like you have designer clothes, you can have designer matter. You could vary these laser beams around and change the shape of this crystal and make things that maybe look like things in nature, but also things that you couldn't make in other ways. And why people are interested in that is it goes back to, well, many people have commented, but in particular Richard Feynman, famous physicist, pointed out that quantum systems are actually quite difficult to model using conventional computers, basically because the atoms are very sort of connected together. You can't break the system apart. But if you had another quantum system, then you can actually model some system you want to look at. So because you can make this quantum system look like other ones, you can explore a lot of interesting things. But that's probably, I don't want to go too much in that direction, otherwise I get a bit technical. But this is the sort of thing that we explore. Another application, again, perhaps slightly futuristic, but is to actually use this quantum matter to build a quantum computer. So the atoms here would be on the surface of some chip, sort of, so not actually touching the glass, but supported off it from by laser light again. So, and then individual laser beams moving these atoms around. This is only just a sort of artistic representation. But the important thing is that because now we've got to very, very low temperatures, we've got something that is very quantum, and we can store quantum information on it and perhaps process it and so on. And there's actually big people working on it at NUS and Nanyang using cold atoms. And the prerequisite for all that is all the laser cooling and BoseEinstein Condensation and so on that's gone before. You have to go through all that to get to the situation where you can then think of these marvelous sort of experiments. Finally, I just wanted to mention one other use, which is sort of more current and actually happening now, and that's, in a non-technical way, to describe an atomic clock. So I just changed the atoms into little clocks. But how does that work? Actually, I won't go into the details of an atomic clock, but actually the primary standard of time throughout the world they are atomic clocks that drive that. So instead of having a quartz crystal like you have in your wristwatch that ticks away and provides the ticks, as it were, for the watch to keep it in time, you use the frequencies of an atom as the ticks that keep the clock in time. And that's great because all atoms, well, a particular species are all the same, identically, whereas all sort of quartz crystals are not exactly the same. So that's very important. And the advantage of using cold atoms in a lattice, here you don't need them one per side, just held there, is that now you've got no Doppler effect. If they were moving around, like I said before, then we measure their different frequency. But if we can hold them still, and we've got rid of that Doppler effect, which is a problem with ordinary clocks, and they're not hitting each other, which is also, upsets the measurement. So cold atoms in optical, held in this little egg box, held sort of steady by light, are a good thing for atomic clocks, and that's just starting to be done now. Okay, so to summarise then, I hope I've given you some flavour of what goes on in this field, and in simple terms shown that if you have an atom and a laser, you can push on the atom to slow it down from very fast to very slow, actually almost stop it moving, almost get to absolute zero. We can get to much less than a millionth of a degree of absolute zero. Okay, to end with a bad pun, I hope you found it a really cool subject, and just some of the details here of where I've got some of the material from. Okay, thank you very much.
I guess we still have some time, so does anyone have any questions for Simple?
Ask the professor, is it what you're saying is that we cannot have a quantum computer running at room temperatures, and also another thing about quantum computers is that if you take into account non-linear terms in the Schrödinger wave equation, then does it affect the logic in the computation process?
Why not try? I can answer the first question. I think it's well, quantum computers, you need them, obviously they've got to work in a quantum regime, so it depends on the energy scale of the system. So typically they do have to be very cold, yes. I mean, I think those technologies for quantum computing, except for the ones that operate using light, or propose to operate using light, then I think anything that's got matter in it, like atoms or ions, or in fact superconducting devices are also used, potentially used for that. They're all cold because they have to be in the quantum regime. And I showed that how cooling, you have to cool, especially with a gas, to a certain value to get into the quantum regime. The bit about the nonlinear Schrödinger equation, I'm not sure that's sort of I can give a non-technical answer to that. But quantum computing is certainly theoretically possible. I think most people think there's no sort of theoretical roadblock to actually realizing quantum computing. It's just really developing our skill in manipulating not just a few atoms or a few whatever system you want to use to make a big system which you can then effectively build a quantum computer out of it. Sorry, I'm not sure that's answered exactly the question. Is there anything else?
I try to understand the definition of temperature for few atoms. For example, let's say that you cool down and you have Bose-Einstein gas in that lattice, and then you move that lattice, and the atoms with the lattice move with it, and it will have a higher velocity. So if you have one atom, for example, you can move it in one direction, you can move another atom another direction, and you can actually, in principle, a mix of atoms going with different velocities means that a higher temperature. But in this case, you have Bose-Einstein condensate, because you didn't do anything. You just start with a Bose-Einstein condensate, you move to lattice. So is it possible in this way to get a higher, like for high temperature you can get?
Yeah, I think I see what you're getting at a little bit. I mean, I talked about the temperature just related to the velocity, but in some sense it's related to the spread of velocities. So, I mean, you could actually have something that's cold, and you could put it in a car or something and drive off with it. So it'll all be moving at a certain speed, but yet relative to... So if you took... well, you could take a BoseEinstein Condensate, I suppose, and put it in a car and drive. It would still be a BoseEinstein Condensate, because the atoms wouldn't be moving relative to each other. They'd have a small spread, but you'd still have sort of a direction, if that's what you mean.
Yeah, that's what I mean.
Yeah, so it's a sort of...
a high temperature. Does this mean we have a high temperature Bose-Einstein gas? Or
No,
is this a temperature?
no, it's the spread of velocities that's important. It's sort of relative to each other.
But you can get like 2, 3 Bose-Einstein gas. I mean, you can start from 0 and move with respect
Yes,
to each
so
other.
yeah, if you took a Bose-Einstein gas, you can. I think people have done experiments like that, where they've taken it and then they've created from it another Bose-Einstein gas which is moving at a certain velocity. So basically, you then end up with 2 Bose-Einstein condensates moving apart. But they're 2 separate condensates. But relative, these atoms are all bunched together and moving not very fast relative to each other, and these are all bunched together, not very fast relative to each other. But as they get hotter, they'll spread out, and then when they stop overlapping, then it would stop being a condensate. I don't know that.
Any other questions?
Applications for the Bose-Einstein condensation.
About applications? Yeah. Okay. Well, I suppose the ones that sort of I mentioned of putting the atoms into the optical lattice and then using that system to sort of model things, and possibly in the future as a quantum computer would be the main ones at the moment. I mean, the various other things in, as it were, scientific applications. There's a lot of things that people want to do with Bose-Einstein condensates. I mean, another thing that people have talked about is making, gyroscopes. I mean, you don't actually have to have a Bose-Einstein condensate for that, but if you think of atoms as waves that you can sort of go around a loop and come back on each other, you can actually make a very accurate gyroscope like that, which might be used for, better navigation. There's some people who work on that, but for the Bose-Einstein condensates, then the things that I mentioned, I think, are the main ones I can think of. Okay.
You mentioned just now about splitting apart the Bose-Einstein condensate into 2 separate PECs.
Yeah.
So I was wondering how exactly you achieve that, since they are essentially a coherent matter wave by itself, a superatom. So how do you cut it into 2?
Well, it's like a technical question, but I mean, well, there's actually quite a number of ways of doing it. Let me just think of a simple one. I mean, I think I can't answer it in a terribly simple way, but I mean, one way is to think of diffraction gratings for light. If you're familiar with that, if you send light, if you have a sort of array of slits, if you send actually light through that, then it'll sort of split up or into different directions. And you can actually do the same with Bose-Einstein condensate, where you send it on something that looks like a diffraction grating, and that actually, when it comes out, it'll actually split up in the different directions, but it'll remain cold. So for each, as I say, in each direction there'll be a thing moving apart without spreading much. Is that?
Yeah, I get your point.
I mean, in fact, with the so-called optical lattices, the ABOX potential is another way of doing it. It turns out if you just sort of switch that on momentarily, it does actually effectively work like a diffraction grating and split the atoms apart without heating them up. So it's actually, in that sense, you could think of a BoseEinstein condensate rather like a laser beam. It's something that's sort of very coherent, if you know what that means. And you could take a laser beam and split it up into other beams using a device.
Thank you. So any last questions? Okay, if not, then let's thank the professor, which was very interesting.